Okay, we're now going to do an example OCTC calculation for a complex circuit, or a more complex circuit than the one we looked at last time. And we'll go through all the capacitors that are necessary. So here I have a common source amplifier, and I've drawn all of the device capacitances as well as some biasing resistors RS, RG, and RD. Now, I can see immediately that CSB is shorted on both sides because the bulk in a common emitter or a common source amplifier is typically shorted to ground, and in this case the source is also shorted to ground. So we can ignore CSB since we don't have to worry about charging and discharging that capacitor. Both ends are tied to the same potential. We can't ignore the other capacitors, so the first thing we're going to do is find tau for CGS. So I'm going to redraw the circuit, and I'm not going to bother drawing a small signal model since we're only going to be looking at the gate node, and we know that the gate node provides us a fairly large impedance, so it won't affect the rest of the circuit. So the redrawn circuit for this analysis, we have RG going to ground after shorting the supply voltage. We have RS going to ground after shorting the input voltage. And then we have the gate of our transistor and the stuff that goes on at the drain we're ignoring. Finally, we're going to replace CGS with a test voltage source and measure the current that would flow out of it. If we do this, we see that Vx over Ix is equal to R CGS, and this is equal to RS in parallel with RG. Hence, the time constant at this node that we'll call tau CGS is equal to CGS times quantity RS in parallel with RG. All right. Now we need to find the time constant for CGD. Now CGD spans the gate to drain, that's the gate to drain capacitance, and I've drawn the small signal model in this case because we're going to have to do a little bit more complicated solution. So we're going to replace the capacitor with a test voltage source, Vx, and measure the current that flows through it, Ix. If we do this, we would find that Vx over Ix, after solving KCL at the gate node and the drain node, would be equal to Rs in parallel with Rg plus R out in parallel with Rd plus Gm times Rs in parallel with Rg times R out in parallel with Rd. And this would be equal to what we would call RCGD. Now our time constant, tau CGD, would be equal to CGD times this RCGD that we just calculated. It's a little bit of interesting algebraic manipulation to get this, and we're going to look at a way to get around having to solve this complicated impedance in the next lecture. But for the time being, we'll move on to the drain to bulk capacitance, tau CDB. Now here, we're not going to worry about what's happening at the gate node, we're just going to worry about what's happening at the drain, so I'll redraw the circuit. We're going to replace CDB with a test voltage source. Measure the current flowing out of it, or into it, depends on how you want to reference it. Now, we know that the output resistance of the transistor is also tied to the drain, so here we have that output resistance. So if we were to measure Vx over Ix, we would find that it would equal R out in parallel with Rd, and hence tau CDB would be the product of CDB and that resistance. Okay, so we have 3 time constants, and what we're going to assume is that they just form one dominant pole. So our pole frequency can be calculated as omega h divided by the sum of those time constants. Okay, and if we were to do a Bode plot of the magnitude versus log of the frequency, we would calculate some gain. We'll just label it A naught. And then we would get to omega h, the pole frequency we just calculated, and the amplitude would start to roll off at minus 20 dBs per decade. Okay. It was a bit of a tedious exercise to do this, especially with the calculation for CDG. We're going to show a method now of how to reduce that using the Miller theorem. And we'll do that in the next set of lectures.